Autoregressive generation is inherently sequential. You generate one token and you use it to generate the next one at a time. This is slow, and the reason is almost frustrating. Your GPU is actually not busy during this process. It's memory bandwidth bound, not compute bound. And speculative decoding exploit this gap. The key idea is almost genius in its simplicity. You use a small and a fast model to make the guesses, and you use a big and smart model to verify those guesses in parallel. Hello everyone, welcome back to my channel. Today we will be discussing 4 speculative decoding approaches. Those are draft target, Medusa, Eagle and Ngram. So let's get started. So let's first understand what problem are we solving. That is the memory bandwidth problem. To process or to generate one token, the model must first load all the weights from GPU memory, that is HBM, into compute cores, then make a forward pass on it and sample one token and then repeat again. For a 70 billion model in FP16, that's around 140 GB of data movement per token. At 2 terabyte per second bandwidth, like for A100 GPU, that's 70 millisecond per token just for like memory transfers. That's roughly around 14 tokens per second maximum, even with perfect compute utilization. So here is the key insight. Whether you run one token or 4 tokens through the model in parallel, you still have to load all the token weights just once. So if you can process multiple token in single forward pass, and most of them are correct, you get a massive speed up for free. So let's now discuss the first speculative decoding technique, that is draft and target. So in this was introduced in 2023 and it works in 3 simple steps. The first one is draft phase. That is a small draft model, example 7 billion parameter model, auto-regressively generates k candidate tokens, and this is fast because draft model is small. The second phase, that is the verify phase. The also known as the large target model, for example 70 billion model, runs one forward pass on all k draft tokens simultaneously. Because transformers can process sequences in parallel, this costs nearly the same as processing one token. And finally, the third phase, that is the accept and reject phase, where the tokens are sampled and compares the target's distribution to draft's distribution at each position using a modified rejection sampling scheme. The math is like, if token I is accepted, then we like check if the random generated weight is minimum is less than the minimum of 1 comma p target of the token divided by p draft, that is probability of target token divided by probability of draft token. And if accepted, we move to I plus 1, that is the next candidate, and sample. If rejected, sample from a corrected distribution and then we stop. Why this preserves distribution exactly? Because the rejection sampling scheme is carefully designed so accepted tokens have the exact same distribution, as if the target model had generated them alone, and zero quality loss. The speed up part is, if the draft model achieves a token acceptance rate alpha, average accepted token per target step will be equal to k into alpha approximately, and typically the speed up is around 2 to 3 times on well matched draft target pairs. The best pairs are like Llama 3 8 billion for the draft and Llama 3 70 billion parameter model for the target. Same architecture family gives higher acceptance rate. Next, we move on to the Ngram speculative decoding. This, like, what if you don't even need a draft model? So this technique helps in that by using the prompt itself as the draft source. The observation is like in long context generations, models often regenerate sequences that already appeared in the input, and like code comments, repeated phrase, and boilerplates, and etc. So the algorithm works like this. First, you build a lookup table from the current context, that is a prompt plus generated token so far. Then you given second step is given the last n tokens, the n grams. Look up what token came next in the context. Then in the third step, you use a draft token, and the fourth step is verify with the main model. No extra model needed, no extra GPU memory. This works remarkably well for like code generation, where you have repeated patterns, imports, and boilerplates. Document summarization, where you have key phrase like appears again and again, and RAG pipelines, where retrieve context gets regenerated, and finally translation and editing, like for source language chunks, where they are repeated in the translation. The famous implementation of this technique are REST, that is retrieval based speculative decoding, and look ahead decoding, that is Hugging Face built-in n-gram speculative decoding. And typically the speed up is around 1.5 to 2.5 in high repetition scenarios. The third technique is Eagle, or efficient autoregressive generation with look ahead, to be like its full form. And it was introduced in 2024. This was a major advancement over standard draft target speculative decoding. And the key insight in this technique is like instead of using a completely separate draft model, Eagle trains a small autoregressive head that operates on the feature level, that is hidden states, not at the token level. And here's why that matters, because in standard draft model generation technique, the tokens first get generated, then converted to embedding models. Gets converted to embeddings, then run through their own transformer, and then they predict next token. But in Eagle draft model, it receives the target model's hidden state as input, and it directly sees the target model's internal representations, making it much better predictor of what the target will do next. The architecture is little different. Like for Eagle adds one transformer decoder layer on top of the frozen target model, and this layer takes like previous hidden state plus current token embeddings as input, and it predicts the next hidden state and therefore the next token. On this like only this one layer is trained, and the rest of the target model is frozen. In like tree based drafting, Eagle doesn't just draft a single sequence, it drafts a tree of like possible features, and multiple candidates continuation are verified simultaneously. For example, from the capital, the sentence, the capital of France is, so branch A will have Paris, which is and so on. Branch B will be Paris, comma the largest, and so on, and branch C will be just Paris and full stop. All branches verified in one target model passes via tree attention masking. The results are Eagle achieves 3 to 5 times speed up on Llama, Vicuna, and Code Llama models. It significantly outperforms standard draft targets and approaches the theoretical maximum speed up. And the further improvement on Eagle was Eagle 2, which like improves this with adaptive drafting, like dynamically adjusting how many tokens to draft based on context difficulty. Now next technique is Medusa, which was introduced in 2024 and takes yet another approach, like named after the mythological creature with multiple heads. So the core idea is it adds multiple independent prediction heads to the LLM's final layer. Each head predicts a token at different future offsets. For example, head 0 will predict token at position t plus 1 as a normal LM head, and head 1 will predict token at position t plus 2, head 3 will predict token at t plus 3, so on and so forth. Typically 3 to 5 extra heads. All heads run in one forward pass, that is in parallel. But wait, future token prediction depends on previous tokens as well. So how can you predict like t plus 3 token without knowing t plus 2? So Medusa makes these as independent predictions, and like they each guess based on previous position t's hidden state alone. This introduces a small approximation. So then tree verification step checks all combination of head prediction against the target distribution. So Medusa 1, which is like additional heads are trained while the base model is frozen, faster to add a slightly quality degradation. But Medusa 2, the base model and heads are jointly fine-tuned and better quality but needs more training. So self-distillation trick is there in this speculative decoding of Medusa. That is, since you don't have a better teacher model, Medusa trains the head using the main model's own output as supervision. This keeps the additional head aligned with the base model, and the result is like 2.2 to 3.6 times speed depending on task, and like it works best on repetitive outputs like code, structural data, and so on. So to compare these, like draft target has as per the extra memory has like is rated medium, or it has extra memory since it trains two model like small and fast. The quality impact is 0, and best is it's used for production high quality tasks. The ngram one, extra memory is negligible since we are using the prompt and the context overall to as the draft model, and quality is again 0, no compromise with the quality, and it's generally used in RAG code and repetitive tasks. The eagle extra memory is smaller as we are adding one extra layer. The quality is again 0 impact, and best is for general like speed up. And the final Medusa, say again we have multiple heads at the end, so memory is again small, but we quality impact is like tiny approximation because we do not know the previous state, and we are predicting it for like t1, t2, t plus 1, t plus 2, t plus 3 states positions, and it is used for batch serving and code. So the recommendation will be like for production serving and no for and where you don't want to compromise any quality, you use eagle. For 0 extra infrastructure, you use ngram, just enable it. And for high throughput batch inference, you use Medusa. And finally, off the shelf with Hugging Face, you use draft target that is built in. Speculative decoding is one of the most elegant ideas in modern AI engineering. You are not just making the model faster, you are making better use of the compute you already have. So all 4 methods are in production use today, as I discussed, like for which task you can use which one. And Eagle is state of the art, and Ngram is free. In the next video, we will discuss static versus continuous batching and why this single change made LLM serving 10 to 20 times more efficient overnight. Thanks for watching. See you next time.